Atul sir? Atul sir? Can
Yes,
you hear
ma'am.
me?
Yes,
Okay,
ma'am.
sir. Shall we start, sir?
Yes, ma'am.
Okay, sir. Okay, sir. A very good afternoon to one and all present. I am Anshul Khanna, Assistant Professor, Department of Computer Science. It gives me immense pleasure to welcome you back here on behalf of Computer Science Department, ABES Engineering College, Ghaziabad. The topic for this session is graphs in problem solving. And this session will be conducted by Dr. Atul Srivastava. Sir obtained his BTech degree in Information Technology from UP Technical University in 2008. He pursued his MTech and PhD degrees from JC Bose University of Science and Technology, YMCA, Faridabad. Currently, he holds the position of Assistant Professor at Amity University, Lucknow campus. His research interest encompasses a wide range of areas, including brain-inspired computing, deep learning, social network analysis, distributed computing, and data analytics. Sir has made significant contributions to the field by publishing numerous peer-reviewed articles in top-tier journals and presenting his research at national and international conferences. He has authored more than 30 research articles in esteemed national and international journals and conferences. Apart from his research and teaching responsibilities, Sir actively engages with the academic community. He holds senior memberships in prestigious organizations such as IEEE, MIA, ENG, and IET. Moreover, he actively participates in various committees and task forces within his department, university, and national and international professional organizations. He has been actively involved in teaching advanced concepts of data structures and algorithms for high salary grossing jobs in the field of IT since last 9 years. Many of his students could grab jobs in big companies like Amazon, Flipkart, Goldman Sachs, and on the package ranging from 23 LPA to 40 LPA. So the topic for today's session will be graphs in problem solving, and the objectives that Sir will be covering are to understand how to model complex scenarios in simplified manner using concepts of graphs, to understand applicability of graphs in various domains of problems, and to understand graph operations and the time-efficient implementations. We welcome you, sir, in this workshop and excited to learn from you. I would now request you, sir, to please continue this session. Over to you, sir.
Thank you, ma'am, for such a warm welcome. Thank you very much, and good afternoon to everyone. So, as ma'am has said that I have been involved in various activities related to academic and research, but I mostly like teaching. Okay, and I have been teaching since many years, and I have been preparing students for higher package jobs for many years. So that is why today I have selected topic graphs. Let me share the PPT. Yes. Okay, so I'll be discussing today. I'll be discussing graphs in competitive coding, and I'll be yes. Vanna ma'am, is there any problem? All right. So so all the participants, see, I actually don't want this lecture to be monotonously, like it should not be one way, it should be both ways. So this lecture should be interactive because I'll be just discussing graph. Okay, I'll not be teaching here, I'll be just discussing because I think that all the participants have less or more idea about graphs. So I'll be just brushing up those concepts, and I will making you understand the simplicity that we have in graph. Okay. For the bandwidth sake, can I just switch off my camera? Is there any problem, Vanna ma'am, if I turn off my camera?
So you can switch off. It's no problem.
Okay, okay, thank you. Okay, let me start. So we are going to discuss graphs. See, graph is considered to be one of the most difficult uh, concepts in data structures or in algorithms, mostly from programming point of view, because graph is very flexible. I must say, it has a wide application range, and it is non-linear. The structure is very complex. So programming the graphs in computer is a bit more difficult thing as compared to other data structures or other concepts of algorithms and data structures. So the graph is considered to be one of the most difficult areas. Okay, and that's why many students prefer to leave graph. Okay, when we study graphs in our curriculum in regular subject, then graph is just covered at the theoretical aspect, and it is not covered at the programming level. And as the algorithms are a bit difficult, so students do not prefer to go into graph. But let me tell you that graph is one of the simplest topics, one of the most scoring topics if you talk about higher package jobs. Okay, see, I'll be talking like I am talking to the students who are aspiring for higher package jobs. Okay, so my today I'll be focused over to higher package jobs, cracking higher package jobs in IT industry, and I'll be discussing the significance of graphs in that. Okay, so suppose a company comes, a very good company, suppose Commvault comes, or any other Flipkart or Atlassian, such companies visit your campus or conduct a recruitment test. They will make you go through a written test, a programming test which has three problems. Okay, so in that three problems, there will be one difficult problem. So all the problems will have different weightage in score. So there will be one hard problem and two medium problems mostly. And that one hard problem, there are 70% chances that that one hard problem will be from graph. So you can see, suppose the test has the test is of 200 marks, then the hard problem will be of 100 marks at least, or 120. It will have weightage of 120 marks, and rest of the two problems will have weightage of 100 to 80. So if you solve one hard problem, then you have scored 50% of the total score. And if you are able to solve one medium also, then your score will be 70 to 75%. So you will be through that written test. Okay, so graph has this capacity. So mostly the hard problem will be from graph, and as because it is considered to be difficult, so companies also know this, that students find it difficult in while coding graphs. Okay, so they put a hard problem from the topic graph. But if you prepare graph, then you will see that it is not as difficult as it is considered, because we have not looked graph the way we should see. Okay, so today I'll be making it easier for you to see that graphs are not actually difficult, they are very simple. Okay, they only look difficult. Okay, so graph is a simple topic in competitive coding. We will go with this thought. Okay, so talking about the problems, when we go through the problems we have related to graphs, generally the problems fall into these three categories. Okay, there can be some other categories also, but mostly they are from these three categories. One category is when we have to find out the connected components in the graph. Okay, so finding connected components is one area where many problems are there. Okay, you will get a problem which is related to connected components, finding connected components. The other area is finding shortest paths. Okay, so when we go through that finding shortest path, mostly in most of the cases, the shortest path problem do not uh, include the weights. Okay, so there are two categories here also in shortest path. Let me write it. See here, there are two categories: when the graph is weighted and when the graph is not weighted. Okay, so if we have a weighted graph, then we have different graph algorithms which you already have studied. Okay, and when we do not have weights on the graph, then the length of the path will be considered in terms of number of hops or number of edges we have traversed to reach from one node to another node or one place to another place. So that will be there also we will try to find out the shortest paths. Okay, so this is another category. Most very good amount of problems are there in this category. Okay, in this category shortest path and in this subcategory not weighted. Okay, we will see that. Then other is reachability, obviously. So there are many problems where we look at the reachability from one place to another place, or one object to another object, or one node to another node. See, I am not always saying that from one node to another node, because we will see the problems which are not from the graph domain, means the problems will not mention anywhere that they are from uh, there is a graph that you have to process, but the problem is from another domain, from some different domain, but it will be solved using the concepts of graph. So there is a big amount of problems which are not from the graph domain, but they are actually solved using the concepts of graph. Okay, so this is the tricky part in graphs, that in the first impression you will not be able to figure out that this problem will be solved using graph, but actually that problem will be solved using the concepts of graph. Okay, so we have to understand that how to figure out that those problems, any problem which is not related anyhow to graphs but can be solved using the concepts of graph. Okay, so first there will be another layer or another layer of programming which says that you will have to convert that problem into graph, and then you will be able to apply algorithms of the graphs over to that converted problem to solve it. Okay, so we'll be discussing everything, but I have just summarized what we are going to discuss during this talk. Okay, so the very first problem that students face is how to start coding for graph. Okay, means how to realize graphs. The first hurdle or first barrier when we have a graph, how to process it, how to program it, how to handle it in programs, is the representation of the graph. Okay, so let me start with the representation. See here I have one example also. So whenever you will have a graph problem in on any online coding platform. Okay, so suppose this is the given graph. So I have this one undirected graph here. Okay, so if this graph is there that you are given as input, so on the online coding platforms or in the programming test of companies, you will receive list of edges. Okay, so this graph will be given like this. So this graph has edge 1 2 1 3 2 3. So these edges are actually given as input. Okay, so you will get the graph in the form of edges. Whether it is directed graph or it is indirected graph, it does not matter. You will get the graph in the form of list of edges. Okay, so the in the input you may be told that the graph has suppose 6 vertices. Okay, so you may be given 6 as input. It will be told in the problem that the first line will have number of vertices in the graph. So 6 is the number of vertices in the graph. Then you will be told that there are 7 edges. So the next line will have number of edges. So this represents number of vertices. This represents number of edges. Okay, so you have basic information about the input, that there are 6 vertices and there are 7 edges in the graph. Okay, now you will receive this edge list. Whatever algorithm you are going to apply to solve the problem will be applied on the representation you create out of this input. Okay, so when you receive edges, you will have to create a representation. You will have to store it. You will have to store it in some format which you can use, which you can process when you are working on algorithms. Okay, when you are applying your method to solve the problem. Okay, so now we will see what are the basic representations for graph and how to uh, create them. Okay, see, when you receive edge, the most uh, popular, or I should say most widely used or simple to use representation is adjacency list. Adjacency list representation. Okay, what is adjacency list? Adjacency list means that we are going to create a list for every vertex. See, do not complicate things. We should not complicate the things. Okay, we are not going to complicate it. We are just going to say that there will be, suppose 6 vertices are there, there will be a list for each vertex. Okay, so we have 6 vertices, 1 2 3 4 5 6. So I will create 6 lists, one for each vertex. So whatever programming language you are using, you can create 6 one-dimensional arrays. There is no problem. So if 6 vertices are given, you know in the input that there are 6 vertices. So you have to create 6 lists. Okay, 6 lists are created. 6 one-dimensional arrays are taken. Number of vertices. The number of arrays or number of lists will be equal to number of vertices. So 6 arrays, simple lists are there. You have created. And then you are going to process the edges one by one. So you are going to receive this one input. Okay. So one input I, j. One input is received in the form of pair of integer values. So two integer values you have received. Okay, there is nothing complex in that. You have received two integer values I, j, 1 2. Okay, so if this graph is undirected, that means 1 is adjacent to 2 and 2 is adjacent to 1. This edge 1 2 says that the vertex 1 is adjacent to 2 and 2 is adjacent to 1. If it is directed, then it will say 2 is adjacent to 1 but 1 is not adjacent to 2. Okay, so as it is undirected graph, that means 1 2 represents that 1 is adjacent to 2 and 2 is adjacent to 1. We are creating here lists for every vertex having adjacent vertices. So this is the list of vertex 1. So 2 is adjacent to 1. So that means 2 must be there in the list of 1. So I will simply add 2 in the list of 1. Okay. And I will simply add 1 in the list of 2, as 1 is also adjacent to 2, as the graph is undirected. So both vertices are adjacent to each other. So I am just entering these numbers. I have received these two integer numbers. I am just entering these two numbers into lists, designated list. 1 is entered in the list of 2, vertex 2, and 2 is entered in the list of vertex 1. Okay, so there is nothing difficult in this. Okay, So you have received two integer inputs, and you have just input these two integers into respective lists. Okay, then you will again receive another pair of integers 1 3, suppose. Okay, so 1 3, that means 1 is adjacent to 3, 3 is adjacent to 1. So in the list of 1 there should be an entry of 3. So next entry in the list of 1 will be 3, and the next entry in the list of 3 will be 1. Okay, so again there is no problem. You have received two integer values. You have just put these integer values into respective lists. Okay, then you will receive another pair of vertex 2 3. So 2 is entered in the list of 3, 3 is entered in the list of 2, because they are adjacent to each other. 3 4 you have received, so 3 will be entered in the list of 4, and 4 is entered in the list of 3. So you are going to receive these edges in the form of pair of integer values. And how many such entries you will receive? 7. It is told in the input that you are going to receive 7 edges. So you can loop this. Okay, you already know that how many edges are there? 7. So you can create a simple for loop which runs 1 to 7. 7 iterations are there for this for loop. Okay, and then suppose this is adjacency list A. So A of 1 dot append 2 when you receive edge 1 2. Okay, or ij, I should write ij. Okay, so ij, you have received this input ij. You are going to append j into list of I, and you are going to append I into list of j. Simple. So this simple 2 3 lines that you write in your program will create this representation of your graph. Okay, the representation that you are going to use when you are going to process the graph, you are going to solve the problem given there on the graph. Okay, so this is very important, because in graphs all the algorithms process the adjacent nodes, because in graph when you are working on a graph, you are at any particular vertex, and you have to go to any other vertex which are adjacent to this vertex. Okay, you can go to any adjacent vertex only. So every time you have to move from one vertex to another vertex, one place to another place, then you will have to access the adjacency list. There is no other option. Okay, so you will create adjacency list. So this is how adjacency list can be created. So this is the first challenge that many students face, that how to handle input. So now you know how you have to handle input. You will receive input in the form of list of edges and process every edge one by one. The edge is nothing but two integer values, two endpoints, two nodes are there. Okay, so if it is undirected, you have to make entries of both of these vertices. So you receive 3 5, then you will enter 5 in the list of 3, and you will enter 3 in the list of 5. Okay, if it is directed, then you know, if ij is a directed edge, then you will enter j in the list of I, but not I in the list of j, because j is adjacent to, in this case j is adjacent to I, but I is not adjacent to j. Okay, so in that case only one entry will be made. If it is undirected, then both entries will be done. Okay, is there any doubt till here? Tell me if anyone has any doubt. See, if you have any doubt, you will just interrupt me and ask your doubt. Okay, because every word I am saying here is very important to understand graphs, because we are starting with very basic things, but they are going to be very complex. Okay, so if you don't understand basics, then graph will still be difficult for you. If you understand the basics clearly, the graph will not be difficult for you. Okay, so if you have any doubt, you should interrupt me and ask your doubt. Okay, and the if the session is interactive, then it will be more beneficial. So if you have any doubt, then you should ask. All right, I think there is no doubt till here. Let me tell one more thing. Say we have created adjacency list. We are going to use adjacency list in most of the problems, but in some problems we are going to need adjacency matrix as well. Okay, mostly where the graphs are weighted. Okay, because if the graph is not weighted, then adjacency list is sufficient for everything. If the graph is weighted, see, if we have weights on the graph, suppose this edge has weight 3, this has 3, this edge has weight minus 2, this edge has weight 10, so something like that. So now you have to uh, store these weights as well. So for to store these weights as well, we are going to use the concept of adjacency matrix. Okay, see, adjacency matrix is nothing but a square matrix of n cross n. N is number of vertices. Here, suppose in this input, the number of vertices is 6. So that means this matrix is 6 cross 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. See, if from programming point of view, if we create two-dimensional array, then definitely the indexing will start from 0. So you will have to be very careful while programming, because suppose the graph is given like this. See, the labels of the nodes are very important when we are coding. Okay, let us understand this. See, the labels are going to be the indexes of our representation. Okay, see, this first list is having the index 1. Okay, so this list is having index 1. 1 is the label of the node. So this list is for the node which has label 1. Okay, so if suppose the starting index is 0, so there is a list at index 0 as well. So this should not be considered the list of the first node. This list will be used if there is a node having label 0. Okay, if there is no node having label 0, then you should not use this list. Leave it empty, leave it unused. Similarly, in the matrix also, suppose the labels are starting from 1 to 6, but when you will create a matrix or two-dimensional array, the indexes will be from 0 to 0. 0, they will start from 0. So if you create a matrix of 6 cross 6, then the indexes will be 0, 1, 2, 3, 4, 5. 6 rows are there. 0, 1, 2, 3, 4, 5. 6 columns are there. So then it will create confusion, because 0 is the first row. You will try to see this matrix as this is the first row for the node 1, but node 1, this node has label 1, then the row number should also be 1, the index should also be 1, not 0. Because if it is 0, then you will have to handle it carefully. You will, every time you will have to see that 0 is 1, so there should be plus 1 or minus 1. Okay, so if such cases are there, the nodes are starting from 1, 0 node is not there in the graph. Okay, then create a matrix of 7 cross 7. 6 vertices are there, 7 cross 7, because you are going to leave this first row, first column unused, because there is no node with label 0. Okay, so you will not use these rows, these rows and columns. Okay, so first 0th row, 0th column will be unused. So we will use from row 1 to row 6, and we will use from column 1 to column 6. So the first column, first row will be left unused. Okay, so this is programming tactics that you will have to use for simplicity, because the simpler the code must be very simple. Try to write simplest ever possible code. Don't try to complex your code. Okay, so if you complex your code, then simple problem will become complex for you. So try to simplify things. Don't handle things in the program manually. The program must be generic. Okay, so if you use the row number 0 and label 0 node is not there in the graph, then you will have to handle it manually, and it will create a problem. If you forget this at one place in the program, then it will not give proper output. Okay, so this should be handled properly. So if 0 label node is not there, then we will not use 0 row, 0 column or 0 list. It will be left unused. We will use from 1. Okay, so every time we will create one extra space, one extra row, one extra column. Okay, so then there will be no problem. So 1 2 is there. So adjacency matrix, what adjacency matrix is? Adjacency matrix simply says that if there is an edge, then the entry will be 1. If there is no edge, then the entry will be 0. So 1 2 is an edge. It is given. 1 2 is a pair of integer values. 1 2 you have received. So 1 2 is an edge. That means 1 is adjacent to 2, 2 is adjacent to 1. So 1 in the row number 1, row for node 1, in the second column, we will put a 1, which represents that there is an edge, 1, 2. Okay, 2 is adjacent to 1. Similarly, in the column 1, in row 2 and column 1, we will put 1, because 1 is also adjacent to 1. If it is directed, then we will make only one entry. Okay, 1, 2. If it is undirected, then 1, 2 and 2, 1. Both entries will be 1. Clear? So this is the concept of adjacency matrix. When we have edges, not weights. But if we have edges and not weights, then this adjacency list is more than sufficient representation. We should use this only. Do not go for adjacency matrix. But if weights are also given, then we should use the concept of adjacency matrix for storing the weights. Okay. So if we have weighted graph as input, then we will receive a triplet. Instead of a pair of integers, every edge will be given as a triplet. 3 integer values will be given. Okay. So in the input, you will see this difference. So if the graph is weighted, then suppose this same graph is given as input, which has weights also. So 6 vertices are there, 7 edges are there. Then this first edge 1 2. So there is an edge 1 2 which has weight 3. So 3 values will be given. Okay, so 3 values will be given, 1 2 3. So first 2 integer values are labels of the nodes, and the third value is the weight of the edge. Okay, so 1 2 is in edge and 3 is weight of this edge. So by using these first 2 values, we will create this adjacency list. We will make 2 entries, 2 into list of 1, 1 into list of 2, and this 3 will be stored in this adjacency matrix. Okay, so we will create list and matrix both. So in matrix, we will make A1 2. So this entry is 3. As it is undirected, so 2 1, this entry will also be 3. Okay, so we will make both entries. If it is directed, then we will make only this entry. Clear? So in this adjacency matrix, we will store weights. So here 3 will be stored, here 3 will be stored. Clear? Similarly, the next edge 1 3. So 1 3 5. So 1 3 is an edge with weight 5. So 1 3, by using these first 2 integers, we will create adjacency list. So entry of 1 will be done in the list of 3, entry of 3 will be done in the list of 1. So adjacency list is updated. 5 is weight of edge 1 3. So A adjacency matrix, suppose A is adjacency, AD is adjacency list, A is adjacency matrix. So 1 3 will be equal to 5. As it is undirected, so both entries will be updated, 1 3 and 3 1 both. Okay, so we will have 1 3 at 5 3 1 5. So these two entries will be there in the adjacency matrix, or we should say it weight matrix. Okay, we will name this adjacency matrix as weight matrix because we are storing weights in that. Okay, so always remember the things that I am telling related to program. Okay, when you are programming, see, writing program for this making entries in two-dimensional array is not a difficult task. Okay, the difficult part is that when you miss the minute things that I mentioned. Okay, those minute things will create problems for you in the graph. Then you will face problem and you will not be able to go through that. uh, you will not be able to understand what is the problem, why your program is not running as it should run. Okay, so always remember these small things. Any doubt till here?
No, sir.
Okay. Okay, so now we have understood the representation. So we are going to use mostly, in most cases, we are going to use adjacency list. In case of weighted graphs, we will use both. Okay. The next important thing, basic fundamental concepts if we talk about, is traversal. See, why I am saying that graph is not difficult, but it is easy. Why I am saying this? Try to understand this. See, if you look at the problems related to stack on competitive coding platforms, you will see a wide range of problems, different problems from different domains, different categories, different approach based problems are using stacks. Okay, the different scenarios are resolved using stacks. There is no set pattern that if this pattern persists, then you should use stack, or you should use tree, or you should use queue. Okay, see, other data structures uh, have this problem that they do not follow any pattern. See, you cannot identify a situation where stack will be used. If you practice well, then somehow you will uh, reach to stack to solve any situation. Okay, but you cannot be sure. There is no pattern, there is no set method, there is no thumb rule that if these conditions are qualified, then you should use stack. Okay, but with graph, this is the easier part. With graph, this facility is available. In graphs, if any problem is there which you are going to solve using the concepts of graph, then all you have to do is traverse the graph. You have to understand only one algorithm, only one logic. If you understand this only one logic, you will be able to solve almost every algorithm in graph. Okay, that is traversal. There are two traversal techniques, BFS and DFS. We all know this. Both are similar techniques, only one basic, very minor difference is there, but very significant difference. We will see that. But you have to understand this very carefully, that traversal is the only algorithm, that is the only logic, is the only skeleton of program that you have to understand to solve every problem in the graph. All the other algorithms, all the other concepts in graph, all the other situations in the graph are actually using traversal algorithms. Your logic, intermediate logic can be different. The decisions can be different. Okay, the processing of the information can be different within the traversal, but the traversal will always be there. If you are finding minimum spanning trees, or you are solving shortest path problems, or you are going to find the components in the graph, in every domain you are going to see that you have to traverse the graph. You are only doing what? You are traversing the graph only. Okay, so if you understand this thing very carefully, then you will be able to solve everything. So if you know how to code traversal, then you can code everything in the graph. The first USP, okay, first, this is the first motivating point, okay, that I have given. That is why graph is simple. The second very important point. Second point is why graph. I say graph is not difficult, it is easy. Easy to score, easy to solve. The optimization, time optimization. See, in competitive coding, in today's scenario, what companies want? Companies want you to write optimal codes. They want you to write time efficient codes. That is why they are testing you like this. Okay, they want you to write time efficient codes. So time optimization is the bigger challenge when you are writing, you are doing competitive coding. See, to reach to correct output is not the difficult part in competitive coding. I always say this. To reach to the correct, see, there are two steps. One is correctness. There are two things when you are doing competitive coding. You are writing codes on online coding platforms. The first part is correctness. The second part is efficiency. Correctness is easy to achieve. This is easier part. Easy. Because you can apply brute force approach. Don't do any optimization. Don't use any good logic. Just do what problem is saying and you will reach to the correct output. Okay. The time complexity can be exponential, but you are not focusing on the time complexity. You are just focusing on the correctness of the output. So reaching to the correct output is not the challenging part in competitive coding. The challenging part is reaching to the correct output in time efficient way. Okay, in best time. So you have to reach to the correct output in best time. That's the challenging part in competitive coding. So time optimization is yet another challenge when you are doing competitive coding. That's why it looks difficult. In graphs, there is this advantage. In graph, you have to understand only one algorithm, which is traversal. If you know how to traverse the graph, then that is more than enough to write any algorithm in the graph. The next is time efficient. That means if you know how to traverse the graph, you should know how to traverse the graph in time efficient way. Okay, so this algorithm, this code should be time efficient. There is very less scope to optimize the logic of BFS and DFS. Very less scope, because you have to reach to every node. So you cannot compromise on that. You cannot skip any node. When you are traversing the nodes, then definitely you are actually traversing the edges. Okay, so there is very less scope to skip any edge or any node. That's why we say that the time complexity of BFS and DFS both is V plus E. V is the number of vertices, E is the number of edges. Okay, so this is the time complexity. You cannot lower this. Means you cannot make BFS or DFS to run in less than this time. It cannot be log V or log E. Okay, so this is the time. Asymptotically, always the time complexity will be this. Practically, we can improve this. We can use a time efficient way of writing BFS and DFS. Okay, so where you can do time optimization, very, as I said, very less scope is there for doing time optimization when we are traversing the graph. Okay, the bookkeeping can be optimized. Bookkeeping. The bookkeeping can be optimized. If we are going to optimize the code for BFS or DFS, then this bookkeeping can be optimized. What is bookkeeping? Bookkeeping means maintaining intermediate results. Okay, maintaining supporting results. That is the bookkeeping. Okay, like when we are traversing, we are going to maintain the distances. Okay, length of paths. So that is bookkeeping. We are going to maintain predecessors. Okay, so that is bookkeeping. So if we if we do this bookkeeping with efficient techniques, then the code will be optimized. So there is very less scope, but very significant. When you are solving the code on online coding platform, then that becomes very significant. Okay, so time optimization, that means you don't have to deal with time optimization you are solving the problem of graphs. So time optimization, the bigger challenge is not there in case of graph problems. That's why graph is very scoring. If you understand graph properly, then you will be able to score easily, because you just have to reach to right decision making. Okay, and you will be able to solve the problem, because time optimization thing is not there. You cannot optimize the code very much. Okay, time optimization is eliminated. Different logics, the possibility of several various logics is also eliminated, because all all you have to do is traverse the graph. Okay, so intermediate, if else some logic, some manipulations are there, then you will be able to reach to the solution. Okay, so I think I have made clear that why traversal is so important for graphs. Okay, and we must understand the efficient way of traversing, means the efficient way of writing code for BFS and DFS. We all know what is BFS or DFS. We should understand that what is the efficient way. See, the most efficient algorithm for writing BFS and DFS is given in the book Corman. Okay, Corman algorithms. This is a very famous book of algorithms, Introduction to Algorithms. And the algorithm for traversal given in this book is the most efficient algorithm for BFS and DFS, because bookkeeping is made efficient in Corman. Okay, it uses coloring. Clear? So I will show you with one example how to do traversal. How you have to write the code for traversal. See this graph is there. So this graph, if this graph is given as input, you will have adjacency list. So there is adjacency list of 1, which has adjacent nodes of 1. So 2, 3 are adjacent to 1. 1, 3 are adjacent to 2. 1, 2, 4, 5 are adjacent to 3. Similarly, 4, the list of 4 has 3, 5, 6. List of 5 has 3, 4. List of 6 has 4. So this is the adjacency list. So if this graph is given as input to you, you will be given the list of edges. You will create this representation. That part I have already covered. Okay, so this adjacency list is there. For every node, there is a list which has adjacent nodes of that particular vertex. Okay, now we are going to traverse it. So when we traverse the graph, we start with any vertex, any source vertex. Mostly the source vertex is given in the problem, or you can decide from your side if it is not given in the problem. Okay, so let us say that we are going to consider 1 as the source vertex. Okay. Now let us go to the part of bookkeeping. See, for bookkeeping, we are going to create 3 storage blocks. Okay, I'm saying these 3 storage blocks. These are simply one-dimensional arrays. Okay, one is color list or color array. Another is predecessors, and the third one is distance vector or distance list. Okay, we have 6 vertices in the graph, right? So in the array there must be 6 spaces indexed with the label of nodes. Try to understand it very carefully. I'm again saying that the index of these locations must be labels of the nodes. So there is one node with label 1. There should be a location in the list of color with index 1. So when in programming, when we create list, then the indexing starts from 0. So there will be a location with index 0, but we have to ignore this. We are not going to use it. It will be there in the list of color, but we will not use it. Okay, we will just waste this one location in the array. That's it. We are not going to use it. We are going to use from location 1, from index 1. Okay, so color, when we are creating the array of color, then it should have 6 locations with 1 to 6 indexing. So that means total the length of this vector or this array is 7. We are going to use 6 locations because 0 is ignored. Because 0 labeled node is not there in the graph. If 0 labeled node is there, then it is okay. Okay. So similarly, in the predecessors also, every node has one reserved location, 1, 2, 3, 4, 5, 6. Here also the 0 will be, the index 0 where location is ignored. So 0, 1, 2, 3, 4, 5, 6. So this index is ignored. Okay, we are not going to use it. We are going to pretend that this array is starting from index 1. Okay, so these 3 arrays, 3 lists will be created, and the labels of the nodes or vertices in the graph are actually the indexes on these arrays. So if we have to see the color of graph 3, then we are going to check the index 3 of this color vector or color array 3. So we can directly reach, see, random access, we can randomly reach to any location in these arrays using the labels of the nodes as index. Okay, so this makes it efficient. Always remember, this makes it efficient. We don't have to traverse, we don't have to search where is node 3. Okay, we know that in color array the location 3 is for node 3, so we can directly reach to 3 to see the color of nodes. Okay, so here in the algorithm, actually the concept is that we are going to use 3 colors. You can use numbers as well. So suppose 0, 1, 2, 3 numbers are there. So 0 is means the node is unknown. 1 means it is explored. 2 means it is visited. You can use any color. You can use white, gray, black, or any other 3 colors. Okay, so you can use numbers or colors, it doesn't matter. You should have 3 codes for 3 possible uh, situations. Okay, so initially the vertices in the graph are unknown. All the vertices are unknown. Okay, so that means all the vertices have this color 0. Okay, or color white. If you are saying it color, then we should use color. You can in programming use 0 as well. So they are white. All the vertices are of white color. We have not visited any vertices, so we do not know predecessors of any vertex. We do not know length of any distance of any vertex from the source. This distance array is going to store the distance of any node from the source node. Okay, see, if you understand this algorithm, then you will be able to solve almost every problem in the graph. Okay, so you should be very careful in understanding this. If you have any doubt, you should interrupt me and ask. Okay, these vectors are very important. To understand these vectors, I am repeating again and again same information because these vectors are very important. When we will see the problems, you will understand why I am focusing so much on this bookkeeping thing. Okay, so we have, see, the core concept here is that we should have one location reserved for each node in every uh, information, like color information, predecessor information, distance information. So we have one location reserved for each node, and that on that location we can reach in constant time. Okay, this is very important thing. Constant time access. So if I have to check what is the distance of node 6 from the source, all I have to just check is the sixth location, index 6 in the distance array. Okay, so it will be done in constant time. This is the idea. Then traversal, you all know what is the traversal. Let me just quickly tell the logic. There is no a big concept in traversal. We will start with the vertex 1. Okay, so when vertex 1 is explored, that means we know this vertex, it is not unknown. We know that vertex 1 is there, which is the source vertex. We have to start from here, and but it is not visited, we have to visit it. So initially the color of vertex 1 is gray. Okay, there is no predecessor because this is the first vertex, and the distance of vertex 1 is 0 because 1 is the source vertex. So this is the initialization part. Okay, so in initialization we will, all the vertices have color white. One is a source vertex, so the color of vertex 1 is gray. Okay, and the distance of this vertex is 0, no predecessor. Clear? Then we will start our traversal. So this source vertex is put in a temporary storage. See, this part is also very important. Try to understand it. We will have a temporary storage because see, we can visit vertices one by one. The algorithm will visit vertices one by one. Okay, so suppose we start traversing, we go to vertex 1. So at a time one vertex is visited. So 1 is visited. When 1 is visited, we know the adjacent vertices of 1 from this list, that 2 and 3 are adjacent to 1. Okay, 2 and 3 are adjacent to 1. So there are 2 vertices. We now have 2 vertices to visit next, but we can visit only 1. So we have 2 and 3, 2 vertices to visit, but we can visit only 1 at a time. So what about the other? So if we visit 2, then 3 is left and will be lost. If we visit 3, then 2 will be left and will be lost. Okay, so we need a temporary storage. This is the most important part of traversals, temporary storage, where we will store the explored node, the nodes which were unknown initially, but now they are discovered, they are explored, and we have to visit them. But we do not have, we can visit only one at a time. If more than one vertices are there to visit, then we will have to store these vertices temporarily in some space. Okay, so we will create a temporary storage to put these vertices which are to be visited next. Clear? This temporary storage, the design of this temporary storage, the way we maintain this temporary storage is going to change the logic or the pattern of visiting the vertices. Okay, there are two algorithms for traversal, BFS and DFS. Everything in both of these algorithms is same. The only difference is the way we create this temporary storage. Okay. So in case of BFS, we use queue to create this temporary storage. In DFS, we use stack. So queue has different insertion and deletion logic. Stack has different insertion and deletion logic. Okay. So suppose we create queue. So in queue, insertion will be done from the rear end and deletion will be done from the front end. We all know this. Okay. So one operation is on the one end and the other operation is on the other end. In case of queue, if we create stack, then both the operation are done at the same end. Okay. So in the queue, the order in which the nodes enter in queue will be followed when the nodes are deleted from the queue. Okay. But in stack, the order will be reversed. The most recent node inserted in the stack will be deleted first. Okay. So if we follow queue, if we implement queue in traversal, then it becomes automatically BFS, breadth first search. And if we follow stack, if we implement stack, it automatically becomes DFS. Okay. So let us see one run of BFS to understand it more clearly and to see how we are going to change these vectors. Okay. See, till now, whatever I have discussed, I have not used any programming concept which is very advanced. We are doing programming in most basic way. Okay. We are just creating arrays. We are just storing information in these arrays. We are updating these arrays. Okay. So suppose one is put in the queue. One is the source vertex. So one will be deleted from the queue. One is deleted. One is visited. One is visited. So color of one becomes black. Okay. See, adjacent nodes of 1 are 2 and 3, both are white. That means they were unknown, now they are explored. So colors will change. Okay. So we will change the color here. So color will be updated. Color of vertex will be updated. This is one thing that we will do. Next thing is predecessor, because these two vertices are explored from node 1. So 1 becomes the predecessor of these two vertices, 2 and 3. So predecessors of these two will be updated. So 1 becomes predecessor of 2, 1 becomes the predecessor of 2, and 1 becomes the predecessor of 3 also. Clear? So predecessor is updated. So that means we started from 1, and from 1 we went to 2, and from 1 we went to 3. This is how it is actually running. Okay. So that means the distance of 2 from the source will be distance of 1 from the source plus 1, because there is just one step ahead. 2 is one step ahead of 1. Okay. So distance of 2, see, we have changed predecessor. Now we have to change the distance. So distance of V is distance of its predecessor U plus 1. Simple. So distance of 2 is distance of 1 plus 1, distance of 1 is 0, as 1 is source vertex. So it will be 1, 0 plus 1, it will be 1, 0 plus 1. So see, we are updating these informations in constant time. Why? Because we are able to access the locations reserved for these nodes in constant time by using the labels of the node as indexes. That's why we can access these locations in constant time. So we are updating these locations in constant time. This is the only optimization possible in traversal algorithms. Okay, so if we create these predecessor and distance vectors, then and color vectors, then it is the most efficient way of implementing BFS and DFS. Okay, so 2 and 3, these two nodes are found from 1, 2 new nodes, unknown nodes, so they are put in the queue. Next, 2 will be deleted from the queue. Okay, because 2 is the node at front in the queue. Okay, so 2 is deleted. So now we are visiting 2, 1 is visited. So 2 has 1 and 3, 2 nodes adjacent. So 1 is already visited because color of 1 is black. 3 is already in the queue because color of 3 is gray. Okay, see, this is the significance of colors. This is the use of colors. We have used these colors to eliminate the possibility of visiting same node again and again. So we are going to visit one node at a time. Okay, that's why we are using color coding. So in the queue or in the stack, whatever we are using, we will add a node in the stack or we will add a node in the queue only if the color of that node is white. That means the node was initially unknown and it is the first time we have explored this node. Okay, so when we visited 3, no new node was found adjacent to 2. So when we visited 2, no new node was adjacent to 2, so nothing is added in the queue. Next, 3 is deleted, so we visit 3, and then we can see that there are two new nodes, 4 and 5, which are adjacent to 3 and the colors are white. So these 4 and 5 will be added in the queue. So the predecessors of 4 and 5 will be updated. 4 and 5 are actually visited from 3. Okay, like this, they are explored from 3. So predecessor of 4 and 5 becomes 3. So these things are updated. Okay, predecessors are updated. Similarly, distances are also updated. So distance of 4 will be distance of 3 plus 1. So 4 is one step ahead of 3. So distance of 3 from source plus 1 is the distance of 4 from source. Okay, so distance of 3 is 1. So distance of 4 will be 2. Distance of 5 will be 2. Okay, distance of predecessor plus 1. Any doubt till here? Then we visit 4 and we get a new node 6 when we visit 4. 5 is already there in the queue. The colors are actually gray. This becomes black. This becomes black when visited. Then we get a new vertex 6 there. So 6 is added in the queue. Okay, and predecessor of 6 is 4. And distance of 6 is distance of 4 plus 1, 3. Okay, so this is how all the nodes are visited now. We have predecessors for every node. We have uh, distances of every node from the source vertex. Okay, so these two vectors, these two arrays are actually output. These two arrays are output of the traversal. Clear? Any doubt till here? If anyone has any doubt, please ask. Does anyone have any doubt?
No, sir.
No, sir.
Okay. Okay, so see, we have these two things as output, because in the problems that we will be given, these two outputs that we have created will answer all the questions given in the problem. Suppose the problem says find the distances, okay, shortest distance in case of unweighted graph without weights. So in graph without weights, the shortest distance is number of hops or number of edges. Okay, so BFS is always going to give us the shortest path. Always remember this. BFS, if we use BFS, it is going to give us the shortest path. Shortest path in graph without weights. Okay, graph without weights, always remember this, graph without weights. If graph does not have any weight and we have to find out shortest path from a particular source, then we should use BFS. These are the things that you should remember. These are the you can say thumb rules of competitive coding. Okay, so BFS is used for shortest paths. We will see the problems. Most of the problems where path is to be discovered, the shortest path is required. Okay, so we should use BFS. In most of the cases, we use BFS. BFS has its own significances. When the length of the path is not the concern, then we can use BFS also. Okay. So if distances are required, there are some problems where distances are to be printed on the console, then we can use BFS and print this distance vector simply. Okay, so it has distance of every vertex from the source. We can directly print it. Suppose path is asked. Okay, the shortest path. Suppose someone says the what is the path from source to node 6. Okay, let us understand this part also. Path generation. This is also very important. Path generation. Always remember that we are not using any advanced concept to write code for these things. We are just simply working on arrays. That's it. Okay. Path generation. Path generation. Suppose 1 is the source node. We have to generate path from 1 to 6. So 6 is the destination vertex and 1 is the source vertex. From 1 to 6 we need a path. So for path generation, there is a very simple logic that we can implement. Take a stack. We will take a stack. Suppose we have to generate path from 1 to 6. We have taken an empty stack. We will put this destination last vertex 6 in this stack. So 6 is put in this stack. Okay. Now we will go to the predecessor list and we will see what is the predecessor of 6. So predecessor of 6 is 4. So 4 is whatever predecessor we get here, we put that in stack. So 4 is also pushed in stack. When we insert something, it is pushed on the top. Okay, so 4 is pushed on the top in this stack. So 4 is there. Now we will see what is the predecessor of 4. See, we have to find out path from 1 to 6. Okay, so until we reach to 1, we will keep repeating this. So 4, predecessor of 4 is 3. Okay, predecessor of 4 is 3. So we will push 3 on the top. So 3 is pushed on this stack. Now 3 is on the top and it is not 1. Then we will see what is the predecessor of 3. So predecessor of 3 is 1. See, we have reached to 1. We can stop here. If we try to find out the predecessor of 1, there is nothing because 1 is the source node. So no predecessor is there. Ultimately, we stop here. Okay. So we have reached to source. We should stop here. Now we should empty the stack and print the nodes in the order. They are deleted from the stack. Okay, so first on the top there is 1 in this tag, so 1 is deleted, print 1, then 1 is deleted, then 3 is deleted, so next node is 3, then 4 is deleted, then next node is 4, then 6 is deleted, next node is 6. Stack is empty. So this is the path from 1 to 6. Clear? This is how we should generate path. So for path generation, this is the simplest way we can generate path. We just have to take one stack, keep pushing the predecessors of the nodes. Okay, then empty the stack, pop all the nodes and print in the same order. So 1, 3, 4, 6 is the path. So in some problems you will be asked what is the path. In most of the problems you will be asked what is the distance. So we have the distance, but in some cases, in some means there are many problems in which the path is to be printed, path from source to destination. Yes, is there any Preeti ma'am, is there any doubt? All right. So now you understand what is the way of generating paths. You can generate paths like this. Okay. You just have to see, this is also very important part of the algorithm, because in many problems, I should not say most, but in many problems, around 40 to 50% problems, you have to generate paths. Okay. So now we have understood the simplest way of implementing BFS or DFS, means graph traversal. See, the graph traversal is very useful algorithm that is used in every problem of the graph. Whatever problem you solve, you will have to use graph. Okay, you will have to use traversal of the graph. Okay, let us now see some problems. Is there any doubt till here in understanding? Okay. Okay, now let us see some problems. Okay, so whatever I have been saying so far, now we are going to see the application of these things. See the problems, there are two categories of the problems on the online coding platforms related to graph, means the problems which are solved using the concepts of graph. One category is of direct problems. The other category is of not direct problems. Okay, it means direct problem means that the graph is mentioned. Graph is mentioned in the problem. Okay, so these are easy to identify. Easy to identify. We can easily identify that this problem is related to graph, because graph is mentioned in the graph, in the problem. In the problem, you are going to receive the list of edges. Okay, from where we started, the list of edges. You are going to receive the list of edges, and from that list of edges, you will create adjacency list, the representation. Then you can traverse it. Very simple. Okay, so there is one category of direct problems related to graph. There is other category which is not direct problems, is the category of problems where problems do not mention graph. Okay, Nowhere. Graph is mentioned nowhere. In the problem, there is not a single mention of graph. You will not be able to recognize the problem that it is related to graph by just reading the problem statement, because nowhere graph is mentioned. The problem is of some other domain. The problem is explaining some situation which is nowhere related to graph. But the problem has some characteristics, has some situational conditions due to which the problem can be solved using graph. Okay, so it is not very easy to identify those problems, but if you practice, you will be able to easily recognize that graph concepts can be used on this problem. Okay, so in these not direct problems, there is one more step required, which is called modeling, which I say it is modeling. Modeling means the graph is actually, the problem is actually not from the graph domain. Nowhere graph is mentioned, but you are going to use the concept of graph, mostly the traversal. You are going to traverse the problem space by using BFS, which is a graph traversal technique. So now you have to convert, you will have to convert the problem space into graph. So that is called modeling, means looking at the problem like a graph problem. Okay, or converting the data or the information of the problem into a graph, or projecting the problem as a graph problem, or projecting the space as a graph. Okay, so that is called modeling. So when you model correctly, this is not a difficult part. The word modeling looks difficult, but it is not difficult. I will tell how is it done. So when you model the problem as a graph problem, then you can easily apply graph algorithms on that. Okay, so very complex problems can be easily solved using graph concepts when you simply model the problem into graph. Okay, let us see some examples of both. See, look at this problem.
ये तो साइन कर रहा है सीएल पे
अरे क्या कर रहा था
अभी आपको साइन कराऊंगा आशीष सर मैं भी आपको साइन कराऊंगा बगल में
Is there any doubt? Okay. See, look at this problem. The problem is on the lead code. You can simply see the problem name is all paths from source to target. Okay, so we have to find out all paths from source to target. We just have to traverse here, and we can see that in the problem it is mentioned that given a directed acyclic graph, you know that a directed graph is given in the input. So the edges are directed, means they have direction. So in edge list, suppose 1 2 1, suppose 0 1 is the edge list. Okay, so that means we know that 0 1 is an edge, 1 is adjacent to 0. Okay, so this is the example of direct problem in which the graph is directly mentioned. Okay, see, this is another example of direct problem, breadth first search. This is the direct problem, most direct problem, because it has mentioned that you have to do BFS. Okay, so shortest reach is also written here. We already know that if we use BFS, we find all the shortest paths. Okay, in the graph which has no weights. So the inputs are actually given as edges. Okay, and we have to traverse it. So in the problem again, directly graph is mentioned. You are going to get the input in the form of edges. Number of nodes are told, number of edges are told, edge list is given, you have to create adjacency list, and then you will be able to traverse it easily. Okay, and produce the output. It is saying that you have to print the distance vector that we had created. We have to print this distance vector simply. Okay. uh, One important thing that I would like to mention here in this problem is that in this problem you can see that this node 5 is not connected to any other vertex. That means this node 5 will be unreachable from the source. Okay, so in that case you have to print -1. So there is a very simple way of doing this. Initially, when you create distance vector, you are told that there are 5 vertices. So you, in the distance vector, there will be 5 locations, 1 2 3 4 5, as I have already told, that if one location is reserved for each vertex. So 1 is source, so distance of 1 is 0, and rest of the vertices have distance -1 because they are not discovered yet. Then when we traverse it, so we get one adjacent nodes of 1, 2 and 3. So distances of 2 and 3 will be distance of 1 plus 1, so 1 1. So they are updated -1 to 1 1. Okay, then we visit 3 and the distance of 4 will be 2, but we will never be able to reach to 5 because 5 is not connected. So if when we create queue here, we can see 1 is there in the queue because it is source, 1 is taken out, 2 and 3, these are two adjacent nodes, 2 is taken out, 2 does not have any adjacent node, then 3 is taken out, 3 has 4 adjacent node, then 4 is taken out, and queue becomes empty. We could not reach to 5 because it is not connected. So the distance of 5 is not updated, it is still -1. So we have to print this. It is very simple. So in C, this problem is easily solved using the concept of BFS. Okay, so whatever we have studied, there is nothing else that we have to do. Here, no time optimization. See, we don't have to optimize the time for this. Okay, we don't have to bother about it. So this is example of direct problem. The problem will mention graph and it will input graph. So these are direct graph problems, easy to identify. Okay. Then let us see that not direct graph problem. So this is a not direct graph problem. See, in this problem, nowhere it is mentioned that it is a graph problem. But let me tell you that this problem is saying that we have a grid. Okay. This is, suppose this is the input. Let me draw this input to make it more understandable, because we have to understand the modeling now. So this is row number 012, column number 012. Okay, and there is an x, which is the hurdle. Okay, so x is the hurdle in the grid. Okay, see, we have to start from here. This is the starting block and we have to reach here. This is the destination block. We have to reach here. The problem is saying that, now see, try to understand, try to uh, pick the pattern here. See, in the problem, a grid is given. First clue is that grid is given in the problem. The next is that it is asking to reach from one block in the grid to other block in the grid. Okay, so if it mentions a grid, okay, number one. Number two, it says to reach from one block to another block, or it says to attack from one block to another block. Okay, then if these things are there in the problem, that means this problem can be solved using the concept of graph. Okay, so in this problem, in this problem, it is saying that we are starting from 0, 0. Okay, we will always start from the first block 0, 0, and we have to reach to the last 2, 2 block. In this case, the last block, destination block is 2, 2. We have to reach here, and it will always mention. Remember this way. This part is very important. It will always mention that how we can move on the grid, because we are now going to model it. To model it as a graph, we have to focus on certain details. Okay, so the most important detail is how we can move. Here you can see in the problem it is written, to your playing piece can move along any row or column until it reaches the edge of the grid or blocked cell. This is the blocked cell. Okay, so that means if the piece is here on 0, 0, in row it can move any long, means it can from 0, 0 it can go to 0, 1, or it can go to 0, 2 until it reaches to the end. Okay, or in this column it can go to 1, 0, or it can go to 2, 0. See, so these are the possible moves. It will always be mentioned in the problem that what is the possible move. Okay, if you have any doubt, if you don't understand anything, please ask, because it is very important. Any doubt? Okay, see, we are going to model it. So the problem is not actually related to graph in any way, but it can be used, it can be solved using the concept of graph. For that we need to model this grid. We need to see this grid as a graph. Okay, so for modeling the grid as a graph, we should, there is one way. What we say that in the grid every block is a node. Okay, see the first formula, first thing, note it down. Every block is a node in the graph. Okay, we are going to see this grid as a graph. So every block is a graph. So it has 9 blocks. Then 9, that means 9 nodes are there. Okay, indexes are label of the indexes of block. The block identification is the index. So every block is identified by using two indexes, I and j, row and column. So those indexes, pair of these integer values, actually is the label of the graph. Okay. One of them, please see there is some disturbance.
So I'm checking.
Yeah. Thank you, ma'am. Okay. See, every node in the graph is considered, every block in the grid is considered as a node, and that node indexes actually become the label of the node. Okay. So we can see that here is a block. This is the first block. The indexes are 0, 0. So this is a node in the graph. We are looking it virtually. Okay. We are doing some assumption or imagination here that there is a node 0, 0. there is a node 01, there is a node 02, there is a node 10, there is a node 20, there is a node 11, there is a node 12, there is a node 21, there is a node 22. So 9 blocks are there in the grid. So 9 nodes are there in the graph. Okay. Now we have to connect, means the edges part. Okay, we have to connect these nodes. So here the conditions to move from uh, one block to another block in the grid will play a very vital role to decide the edges. Here we can see that it says that we can move from any block to any other block in the same row. Okay, any long means from 0 0 we can go to block 01 or we can go to block 02. So that means there is an edge from node 0 0 to 01 and there is an edge from 0 0 to 02. So these two nodes are actually adjacent to 0 0. Similarly 10 and 20, these nodes are actually adjacent to this node. Okay, so when we will do traversal, okay, suppose we are going to traverse, means we are going to traverse this grid as a graph. So what we will do, suppose we are going to do BFS. So we are going to start from this block 0 0. So this is a node, so 0 0, this pair is actually put in the queue. So we will make a queue such that the element of the queue is a pair of integers. Okay, so 0 0, this node is actually put in the queue. Okay, now we will start the traversal. So 0 0 is deleted from the queue, so node 0 0 is out. Now we have to find out the adjacent nodes. So we don't have to create adjacency list. See, this is the most important part. We don't have to create adjacency list in advance for such cases. We will generate adjacent nodes run in runtime. Okay, so 0 0 is out, 0 0 is out. We know that we can move in the same row or in the same column, okay, for any distance. Then that means we know that if we move in the same row, then this column number will be incremented. So 0 1 and 0 2, row number will be constant. So 0 1 and 0 2, these two nodes are adjacent, so these two entries are done in the queue. Okay, because 2 is the limit. Clear, we cannot go beyond 2. Similarly, in the column direction, the column number will be fixed, row number will increment 1 and 2. So 1 0 and 2 0, these are two adjacent nodes. Clear, so these two adjacent nodes are actually put in the queue. These adjacent nodes are generated by using the conditions for movement on the grid. So this condition is very important. So these adjacent nodes are actually generated. We do not create adjacency list in advance. We generate these adjacent nodes in advance in runtime. Okay. So this is the very important part that I have told you. Let me tell you one more important point. We have to create predecessor and distance, these two things, these two vectors. Okay, so in case of grids, when we solve grid problems using graphs, then these predecessor, in normal graphs we create one-dimensional arrays, but in case of grid, the predecessor storage is also a grid and distance storage is also a grid. So in grid we have a facility 0 1 2 0 1 2, grid of same size 0 1 2 0 1 2. So 3 cross 3 grid is given as input. So 3 cross 3 grid will be there for predecessor, 3 cross 3 grid will be there for distances. Because we have 9 nodes here, we have 9 nodes here, same indexes and same labels. So the labels are used actually as indexes we have discussed it, the node label must be used as indexes in the predecessor and distance uh, list or grid. Okay, so these predecessor and distance grids will be there, means two-dimensional array or matrices will be there. Okay, so when we visit 0 0 and we know that adjacent vertices are or adjacent blocks are 0 0 0 1 0 2 1 0 1 2 0, so that means 0 1 predecessor of 0 1, this block, okay, is 0 0 because we can reach here from 0 0, and predecessor of 0 2 is 0 0. So we will make this entry on this grid. 1 0 is 0 0, 2 0 is also 0 0. So now we are storing the predecessor. Predecessor is pair of integer values. Okay, the vertices or nodes are actually indexes. Clear? Similarly, distance. So distance of 0 0 is 0. So the distance of 1 means 0 1 will be 0 plus 1 is 1 1 1 1, because predecessor of all these four blocks is 0 0 and distance of 0 0. So distance of these will be plus 1. Clear? So this is how we update distances. This is how we update predecessors. This is how we generate adjacent nodes. Clear? So when this algorithm terminates, we will have again predecessor and distance matrices in this case. Path generation is same, distances are same. So in this case, the problem is saying that we have to reach to the last block, that is 2 2. So whenever in the queue 2 2 is generated, 2 2 is entered, 2 2 anywhere, from anywhere, if 2 2 is generated and put in the queue, the predecessor of 2 2 will be set here and distance will be stored here. We have to stop because we are searching for 2 2. We don't have to wait till the queue gets empty. Okay, we can terminate the search in between when we reach 2 2 or the block we are looking for. Clear? We can stop at that point. So whenever 2 2 is generated and entered in the queue, we can stop, and then we can start generating the path from here. We can see that from 0 0 we can go to 0 2, and from 0 2 we can go to 2 2. So from 0, when we visit 0 2, we actually can go to 2 2. So 2 2 will have predecessor 0 2. Okay, so 0 2 to, if we try to generate the path, so 2 2 has the predecessor 0 2 and 0 2 has the predecessor 0 0. So the path will be 0 0 to 0 2 to 0 2. So this is the shortest path to reach from 0 0 to 2 2 in two hops. The distance will be 2. So this is how we have to generate the solution. Clear? So is there any doubt? Is there any doubt?
No, sir.
Okay. So this is a long topic. Let me show you one more example because we are running short of time. See, the topic is not difficult, but it is lengthy, obviously. When you understand this, then you will be easily able to solve it. Okay. See, this is another similar problem. Here again, grid is given. Okay. Here again, it is asking a path. It is asking to reach from 0 0 to the last cell. Here the condition to move over the grid is different as compared to the previous problem. It is saying that we can move to the block which has 0. Okay, only. So suppose we are at this block. So then we can move to any adjacent block which has 0. Okay. So it has 0, so we can move here. It does not have 0, it does not have 0, so we cannot move here or here. So from here we can move here or here because they are 0, they contain 0. Clear? So while generating the adjacent nodes, we will have to check these conditions. So suppose we are at the block ij. So we can move one block on the right, one block on the left, one block on the down, one block on the up, one block on diagonal, means total 4 blocks will be there on diagonal. So we can simply see that this is ij plus 1, this is ij minus 1, this is I minus 1j, this is I plus 1j, this is I minus 1 j minus 1, this is I plus 1 j plus 1, this is I minus 1 j plus 1, this is I minus 1 j minus 1, this is I plus 1 j minus 1. Okay, so we have to check these 8 conditions, and whichever block from ij, whichever block has 0 stored will be adjacent to ij. So if it has 0, it has 0, it has 0. So these 3 blocks will be adjacent to ij. Okay, so when we are actually running the BFS logic here, so when ij is picked from the queue, so these 3 entries will be made. So I minus 1, j minus 1 will go in the queue, I minus 1, j plus 1 will be put in the queue, and this ij plus 1, suppose ij plus 1 will be put in the queue. Rest of the adjacent locations will be ignored as they do not contain 0, they have 1. Clear? So these are the adjacent ones. Then again we will pick one from the queue. See, the same logics, we are doing everything same, we just have changed the way we move on the grid. See, you can see the simplicity that one code is applicable to everything. Again, the predecessor will be a grid of same size, the distance will be a grid of same size, no problem. Okay, so everything is same. The only condition to generate the adjacent node, that condition has changed. Nothing else has changed. The same code from the previous problem can work for this problem as well. Clear? Any doubt till here? All right, I think I should stop here. Vanna ma'am.
Thank you, sir, for such an excellent session. It was indeed a very informative and interactive session, and I hope that all must have learned from the session. If anyone is having any query, then you are free to ask now. Anyone, if anybody wants to ask anything to sir? Maybe once again,
Good
thank
evening, sir. Good
yes.
evening, sir. I just have a very simple question.
Yes.
Can you please explain which traversal algorithm requires less memory usage and why?
Which algorithm requires less memory? BFS and DFS you are talking about?
Yes, sir. Which traversal algorithm?
Okay. See, okay, let me find a blank page. Then I will explain. Okay. Okay, let us take one simple acyclic graph. Suppose this tree is also a graph. Okay. Suppose this is the source node we have to traverse. Suppose when we are doing BFS, the algorithm will visit the vertices like this. It will go from here to here and these vertices. Then it will go from here to here, these vertices. Okay. So suppose the node that we are searching is here. So destination node is here. Okay. We will stop when this node is explored. Okay. So this node has the path from S to suppose 1, 2. So S to 2, 2 to D. Clear? So we are visiting S, then we visited S, then we visited 1, then we visited 2, then we will visit adjacent nodes of 1, which are these nodes. then we will visit adjacent node of 2. So in the queue, S 1 will be stored, 2 will be stored, then this node 3, 4, 5, 6, suppose. So 3, 4, 5, 6, these will be stored. Okay. So in that case, we will have to store everything because we don't know where the destination node is going to be. Okay, so we will have to store every path. That means we have explored this path, we will have to store it. We have explored this path, we will have to store it. We have explored this path, we will have to store it. We will have to store it this as well. Okay, because the destination node can be somewhere here also. So all the paths are stored. Clear? So we need more memory in case of BFS. Let us see what happens when we are doing DFS. So suppose when we are doing DFS, suppose we started here, then we went here because it goes in depth first. Then it goes here. And this is the last node. This is the last level. And we have not found the node we are searching for. Then we know that this path does not have the node that we are looking for. So we will return back from here and we will explore the other node. So in that case, now we can forget this. Okay, we don't have to store because we certainly know that the destination node is not there. Is it clear? But in case of BFS, we can never be sure that this path is not going to have the destination node. So we have to store everything. So that's why BFS requires more memory, DFS requires less memory. So if n nodes are there, suppose we have taken a cyclic graph, which is a tree. So these many paths will be stored, but here we will have to store the we can say the depth of the tree. Okay, whatever the maximum depth, that is the amount of memory we need. Is it clear?
Yes, sir, it is clear. Thank you, sir.
Anybody else wants to ask anything?
Yes, ma'am.
Please.
सर BSF और DSF का एप्लीकेशन क्या हो सकता है?
See, in the whole lecture, we were actually discussing about the applications. Okay. See, BFS and DFS, these two strategies are actually to the discover the required node or required result in any space. Okay, so suppose we have a space, so this is a space, we have to search it. So how will we search? We will search using BFS or DFS by converting this space or by interpreting this space as graph. Okay, so let's see this is the space, this is a grid is an space. Okay, so this is a space which is given. We have modeled this space as graph and now we are searching in this graph. Okay, so in real life, if we talk about, most of the complex problems are solved using the concepts of graphs, because we can convert every situation where there are connectivities between different possibilities, different possible situations. If we have a conversions from one situation to another situation, we can represent it using graph and we can apply graph algorithms to that. Okay, so graph algorithms or traversal, BFS and DFS, they have several applications in almost every field, possible field. Okay.
Okay, sir.
Anybody else wants to ask any question? Okay, we once again thank you, sir, for sparing your valuable time for the session and for dispensing valuable knowledge to us. I also thank all the participants for attending the session. Thank you, sir, once again. You all can
Thank you,
disconnect.
everyone.
Thank you all. किया था।
Dear participants, now we'll share quiz and feedback link on WhatsApp group. Kindly attempt the quiz and give your valuable feedback.